Hello students, this is the 12th video lecture on metric spaces, and in this lecture we are going to study the Cantor's intersection theorem, which is very important theorem in this paper, that is metric spaces. So Cantor intersection theorem statement is given here, that is let XD be a complete metric space and let Fn be in decreasing sequence of non-empty closed subsets of X such that d of Fn tends to 0 as n tends to infinity, and then intersection of Fn n from 1 to infinity contains exactly 1 point. So in this theorem, what is given? One metric space is given. Which type of metric space is given? That is complete metric space. All of you know that. What do you mean by complete metric space? Metric space is said to be complete if every Cauchy sequence in it is convergent. Then we said that that is the complete metric space. Now other things which are given are here we consider one sequence Fn, that is the decreasing sequence of non-empty closed subsets of X such that d of Fn tends to 0 as n tends to infinity. And then we have to prove that this intersection of Fn n from 1 to infinity contains exactly 1 point. So let us try to write the proof for this theorem. Before starting the proof for this theorem, we will clear some points which are required, that is the decreasing sequence. In the last year syllabus there was an article, that is the decreasing sequence. So let us see what is meant by decreasing sequence. Decreasing sequence, or in other words, that is the non-increasing sequence. Non-increasing sequence. Suppose there is one example, -1. This is suppose S1, S2 is equal to -2, S3 is equal to -3, and so on. And this is the sequence denoted by this. Now here the first term is -1, second term is -2, and second term is less than first term. Third term is less than second term, and so on. So in this case, Sn plus 1 is less than or equal to Sn. Or in other words, we can say that here, the Sn plus 1 is proper subset of Sn. Sn plus 1 is proper subset of Sn. In this case, this is the decreasing. Similar concept for the increasing sequence. That is, if we take 1, 2, 3, 4, and so on, this is the increasing sequence. It means the next term is greater than first. That is so in this case, this Sn is proper subset of this Sn plus 1. Is proper subset of Sn plus 1. So these are some concept of the decreasing and non-increasing sequence. Now let us prove today's theorem, that is the Cantor's intersection theorem. Now here what is given? It is given that the given sequence Fn is a decreasing sequence of non-empty closed subsets of X, and it means this Fn is clearly non-empty. Clearly it is non-empty, and as it is the non-empty, therefore we can construct more sequences which are the subsets of this. So we can choose the sequence of points xn such that this xn belongs to this Fn, and for n is equal to 1, 2, 3, and so on. This And now our aim to show that this sequence Xn will be a Cauchy sequence. Will be a Cauchy sequence. Now, this sequence Fn is decreasing sequence, and therefore this Fn plus 1 is proper subset of Fn for all n. And therefore here xn, xn plus 1, xn plus 2 and so on are all lie in Fn. Are all lie in Fn. Also, what is given in this theorem? Next point, d of Fn tends to 0 as n tends to infinity. Now, what is d of Fn? D of Fn means that is the diameter. That is the diameter. We have taken definition in our first video lecture. That is the diameter. So, see that. And therefore, for epsilon greater than 0, there exists a positive integer m0 such that this d of Fn is less than epsilon. D of Fn is less than epsilon, and which implies that xn0, xn0 plus 1 and so on all lie in Fn0. All lie in this Fn0, and therefore we have this d of xn, it is less than or equal to d of Fn0, and d of Fn0 is less than epsilon. So by this condition, it is clear that this xn is a Cauchy sequence in capital X. And what is capital X? It is the complete matrix space, and here this sequence xn is a Cauchy sequence in that capital X. And therefore it is, we can say that this xn is a Cauchy sequence, and as it is given that X is complete matrix space, and therefore this Cauchy sequence is convergent. Convergent means it must converge to some limit, or we can say that is this sequence xn, this converges to x, or in other words we can say that this limit xn n tends to infinity is equal to x. And now come to the next part of this proof of this theorem. Now we have to prove that this x belongs to intersection of Fn. But what we have to show in this theorem? We have to show that the unique, exactly one point means unique, and we know that we have studied if limit xn n tends to infinity is equal to, suppose L, limit xn n tends to infinity is equal to m, then this both are not different. That is, this L must be equal to m. It means the limit of a sequence is always unique. So by this theorem, by this result, it is clear that this x is unique. But now just what we have to show? We have to show that this x belongs to intersection of F. So now we will show that. Now we will show that this x belongs to intersection of Fn, n from 1 to infinity. And we will prove this by method of contradiction. So for that purpose, suppose x does not belongs to this intersection of Fn, that is n from 1 to infinity. Suppose that x does not belongs to this Fn n from 1 to infinity. It means there must at least one m such that x does not belongs to that. Therefore, there must exist a positive integer m such that x does not belongs to that fm. Does not belongs to fm. Now, what type of sequence fm? It is the sequence of closed subsets, and therefore x does not belongs to m. It means this d of x m will be greater than 0. Greater than 0. So let this d of x fm is equal to suppose r, and that is greater than 0. That is greater than 0. Then d of xy is greater than or equal to r. How we have written this? How we have written this? D of x fm. Fm means set. Fm means set, and this is one point y. It means we have to write here for all y belongs to fm. For all y belongs to fm. fm हा सेट आहे. d of x fm greater is equal to r greater than 0. y हा आपण याच्यामधून घेतलेला आहे. प्रत्येक एलिमेंट साठी हे व्हॅलिड व्हायला पाहिजे. फॉर एव्हरी एलिमेंट दिस d of xy, if we take suppose z belongs to fm, then also this d of xz is greater than or equal to r. So this d of xy is greater than or equal to r. Now thus the open sphere S r by 2 of x and fm are disjoint, because open sphere means less than or equal to r definition. So this S r by 2 of x and fm are disjoint, and therefore n is greater than m, and which implies that this fn is proper subset of this fm, and which implies that this xn belongs to fm, because this is proper subset of this, and this is belongs to fm, and therefore this must be belongs to this fm, and which implies that this xn does not belongs to s r by 2 of x. But this is not possible, because the sequence xn converges, and therefore x must be belongs to this intersection of fn n from 1 to infinity. So in this way we have proved that the intersection of fn n from 1 to infinity contains unique point, that is exactly 1 point. Now finally we have to show that this x is unique. If possible, suppose let y be another point in this intersection of fn n from 1 to infinity. We have to prove that exactly 1 point, but here also we are using the method of contradiction. So let y be another point in this intersection of fn. Then what will happen? As y belongs to intersection of fn, it means y must belongs to fn for every n, because we know that the set theory, if x belongs to some intersection of that point, then it must belongs to every element, every set of both. That is like this, x belongs to a intersection b, which implies that x belongs to a and this x belongs to b. So here also y belongs to intersection of fn, it means y belongs to fn for every n. So which implies that d of xy less than or equal to d of fn. D of xy less than or equal to d of fn for every n. This is my definition of diameter. You see that definition from our first lecture, that is the diameter. But what is given here? this d of fn tends to 0 as n tends to infinity, and therefore taking limit here, d of xy is less than or equal to 0. d of xy is less than or equal to 0. But we are studying the metric space, and one important property of metric space, that is d of xy must be greater than or equal to 0. This is one argument, this is second argument. So by combining these two arguments, d of xy less than or equal to 0, d of xy greater than or equal to 0. So combinedly, which implies that d of xy must be equal to 0, and there is one more property of metric, that is d of xy is equal to 0, which if and only if x is equal to y, and it means we have shown that x is equal to y, and therefore the x belongs to that intersection of fn is unique. That is exactly 1 point. So this is important theorem. So here we stop this lecture. On 28th October there will be multiple choice question test, and the link will be given on the same day, that is the 28th October. So watch all the videos and study. So here we stop.